This week, we're talking about fluid mechanics. Sounds impressive, but in fact, it's not that complicated. We're going back now to build on material that you learned in 6A, which in many ways is simpler, more intuitive, more familiar than waves and electromagnetic radiation things that we did in 6B. So I think you'll find this not too difficult if you're able to change the way you think about objects when you deal with fluids. If you can handle that transition, then you should have no big problems with this week's material. First, little jargon. You're used to, I'm sure, the definition of density, which is very, very important in physics. It's just the mass divided by the volume. Hardly even needed that formula up there because I'm sure you knew it anyway. Our units, of course, are going to be kilogram meter units, so that means that mass will be measured up here in kilograms, and the volume then is a cubic meters, three-dimensional volume. I grew up learning the old centimeter gram units, and the density was fairly nicely set up in those days to be keyed, as all metric units are, to the density of water. And so I always remember that the density of water at the point where it gets as dense as it's going to be, which is just a little bit above freezing at 4 degrees centigrade, that density is defined, this is the basis of the metric system, to be 1 gram per cubic centimeter. Now with our somewhat clunkier units here of kilogram meters, we're going to have to take into account, let's see, there are 1,000 grams in a meter in a kilogram, so the mass goes up. But then, of course, 100 centimeters makes a meter, and there are 3 dimensions, so you have to cube that. 100 cubed is 1,000,000. So we have 1,000,000 cc's in 1 cubic meter. The result is that these nice convenient densities, like the density of water, 1 gram per cubic centimeter, get multiplied by 1,000 to give the new kilogram per cubic meter units. That's a pretty big number, but hopefully you can keep track of it. And if you don't like keeping track of 1,000 kilograms per meter cubed all the time, other people don't like doing it, a shorthand that people have adapted in this field in fluids is the so-called specific gravity. Sounds complicated, but it's not. It's just the ratio of the density of that material, that fluid, for example, like alcohol, for example. That's one that people measure very carefully, the density of, as a proportion to the density of water. In other words, specific gravity of 0.95 means that alcohol is 95% the density of water. So it'd be 950 kilograms per cubic meter. So we might use that terminology. At least I would like you to know what that terminology means. No new physics in there, whatever. There was no new physics on that slide at all. There's no new physics on this slide either, but let's just see if you're comfortable with it. We've got a solid iron sphere of radius 18 centimeters. That's a typical wrecking ball. What's the mass of that? You might be surprised. It's really a lot for just something that big. All we have to do, of course, is to know the specific gravity or the density of iron. So I'm looking it up in our table 13.1 of our textbook. See, we're back now in the earlier chapters because this is really just building on 6A mechanics, just fluid mechanics. And I see here that iron has a density of 7,800 kilograms per cubic meter, right? 7.8 times the density of water. And so what does that give us then in our particular problem? Well, you just plug in the volume of a sphere. The radius is, let's do this in cubic meters, 0.18 meters. Cube that on your calculator, multiply it times 4 pi over 3, and you should come up with something like a volume of 0.024 cubic meters. Not very much, but we're multiplying that times 7,800. So we have a number here that's a little less than a 40th times a number that's almost 8,000. It should come out to a little bit less than 200 kilograms, and the exact answer, I think, on your calculator should come out to 190 kilograms if you're punching in the numbers right. So I would not have a exam problem that just asked you for something so trivial, but that might be the first step in working out something on an exam problem, and so it's 1 point off if you get that wrong. Here's a somewhat newer thing that you need to learn for this chapter, which is the definition of pressure. And again, it's one of those words that has a human context, and so it's used in many different ways in literature, in emotion, and so on. Forget all that stuff. We're just going to go with a physicist definition. And the physicist definition is pressure is a force divided by unit area. So all that stuff about, oh, I'm just under so much pressure in this course and so on. Well, you know, from a physicist's point of view, we are actually under a great deal of pressure. All of us, and it's all the same as long as we live at the same altitude. In Los Angeles, yes, we're under a lot of pressure, but let's see if we can calculate it. And so try to clean your mind of all of the other baggage, emotional baggage that pressure carries with it, and just measure it, force per unit area. In our units, MKS units, we want the force to be measured in newtons, we want the area to be measured in square meters. So I'd give you full credit if you just give me a pressure in newtons per square meter. Just to have another unit so that you know what these units mean, it's rather appropriately measured. We measure pressure in units of pascals, because he's one of the founders of fluid mechanics now, so that's a nice honor for Pascal. 1 Newton per square meter is 1 Pascal. Right, so you should know that. Now that we have that definition, let's do a very, very simple example, but there's actually a little bit of interesting content in this. What is the pressure on your 2 feet? Let's take a little optimistic mass estimate for a person, only 60 kilograms here. And then if you look at your feet, a typical foot might have an area of about 250 square centimeters. And if you're standing on 2 feet here, you're probably distributing the weight very equally between the 2 of them. What if you're just standing on 1 foot here? I'm just going to do the second problem here, part B. Obviously, if you stand on only 1 foot, you still have the same amount of force that must be provided, but now it's only by half the area, so twice the pressure on 1 foot. I honestly do not know how flamingos do it. I don't know why they do it. That's some issue about evolutionary biology, which is, thank goodness, not covered in this course. But anyway, if you do decide to put all of your weight on 1 foot, what kind of pressure are we talking about? Well, there's the force, which is just mg. There must be an mg force of pressure on the floor holding you up so you don't collapse through the floor. Well, there's mg, 60 kilograms times g. I approximated here. I always do, don't I? Technically, it's 9.8 meters per second on the surface of the Earth. Pretty much I'm going to always be assuming g is just on the surface of the Earth here, because that's where all of the MCAT problems, all of the biological problems, medical problems, I mean, we don't do these problems in space. I've never seen an MCAT problem that had you doing this on the moon or something like that. Lunar medicine would be a mess anyway. So we'll keep this very simple. mg is 600. We divide it by the area. Just make sure that you've transferred the 250 square centimeters into square meters so that we have consistent units, so we can get this in newtons per square meter, or else you'll get it wrong. You'll get a point off there. Anyway, when you divide 600 by a 40th, you get, wow, a lot of pressure there on that 1 foot, 224,000 pascals. That is a lot. It's amazing, by the way, that a little foot can withstand that much pressure all day long, day after day, year after year. It's a beautifully designed mechanism, really better than we can design, actually. Isn't evolution and biology just wonderful? Sometimes it is. I'm just very impressed by the foot. But that's not really what we are interested in here. We're mostly interested in the pressure in a fluid. And this is something that is different from your foot, which is more or less like a solid. And this is not intuitive. This is the one new way of thinking that you have to get into your mind when you're thinking about fluids that we weren't doing in the previous chapters on just classical mechanics, which deal with solid objects like blocks, for example. Well, if you have a block, let's say a 1 centimeter by 1 centimeter, 1 centimeter block, everybody knows what happens when you push on it. But when you push on a 1 centimeter, 1 cc cube of water in a fluid, it's a very different situation. It's kind of a little bit surprising here. So here is a 1 centimeter by 1 centimeter by 1 centimeter cubic centimeter of water in a glass of water there. And let's contrast the situation. Suppose that I had, let's say, for example, a cubic centimeter of ice. The same thing, almost the same density. If you push very hard with your finger down on a block of ice, there'll be a very strong force down, and you know what's going to happen. It's in a rigid crystal lattice structure. Things can't move at all. The molecule, well, they can move a little bit, but they can't really get out of that structure. So you compress the structure on the top, it pushes on the bottom of the structure, pushes all the way through, and you end up with a force going all the way transmitted straight down through the ice, and it's pushing on the table, for example, if you push it there. So push on a block, and all the force is transmitted in the same direction that you were pushing on. Totally different for fluids. Fluids don't have any fixed shape, any fixed volume. It just depends on what container they're in. What happens if that ice were turned into water? Of course, you push on water. Well, that's what's happening here. There's a cubic centimeter of water in the jar, and if you push on one direction, the water splats out in all different directions, because molecules, unlike in a solid, in a fluid or a liquid in particular, the molecules can slide around each other, and so the force ends up pushing things sideways in all different directions. So the difference is then that pressure is the same in every direction for inside a fluid. So this is completely different from what you would think when you push on blocks, the kind of problems that we had in Physics 6a. Now we're in a new regime here, and so one result of this is then, well, it's shown by the arrows. It has to be that way, actually, in a fluid, because well, let's just look at this. Here's the amount of pressure pushing on that cube from the left. It has to be exactly balanced by the pressure pushing on that cube from the right. The force from the left, the force to the right, they have to cancel out. They have to add up to 0. Just as the force from the back has to balance out and cancel the force from the front, the force from the top has to cancel out the force from the bottom. We're going to look at that a little more carefully here. Because if those forces weren't balanced, if they weren't canceling out, if they didn't add up to 0 using vector addition, then there would be a net force which would cause this fluid to move around somewhere. But that's not the assumption. It says static in here. In these problems that we're looking at, we're just looking at a non-moving fluid. So there's no acceleration, there's no unbalanced forces. And so that's a difference that's important to keep in mind. Let's look at that a little more closely. How about the force then between the wall that confines the fluid, the container of it, and the fluid itself? In general, if you had two solid objects here and there was friction between them, like if that were a solid cake, this blue cylinder of some kind of frictional material, and it was rubbing against the side of a jar, then in general, thinking back to Physics 6a, you would draw the force between the blue object and the wall of the container as a force maybe going, for example, in this general direction here, a pink vector, and you would break it down into two components. As you're familiar with, there would be one component which is perpendicular to their boundary. It's exactly perpendicular to the wall of the container. And then there would be a parallel component which runs sideways along the wall of the container. There is no parallel component when you have a fluid, because if you try to move a fluid sideways, the molecules will just slide by each other. There's no friction there at all. If there were a non-zero parallel component of the force between these two objects, the blue stuff and the glass wall, then the fluid would start moving, which we've already said is not happening. We have a hydrostatic situation. So we always know that the force between a fluid and any boundary surface that's in contact with it is always going to be exactly 90 degrees, exactly normal to the surface where the interface is, like the surface of the container. So that's actually a simplification. It's good to keep that in mind. So forget the parallel component. All of the force, which of course translates to a pressure if you just divide it by a unit area, all of the force or all of the pressure is exactly perpendicular to the boundary that you're looking at where the force is acting across. That's a great simplification, which, by the way, would not be true for complicated, non-ideal fluids that are sticky, have viscosity, honey, things like that. So let's not do them in Physics 6c, all right? That's too much trouble to deal with. Good. Now here's the money situation that we need to look at carefully. I've got fluid in a box, and I'm going to single out one rectangular cube of fluid, and I have a very simple question here. What is holding it in place? There must be a balance of forces, zero net force, because nothing is moving, nothing accelerating, an equilibrium condition. That means all forces balance and add up to zero. Let's look at this. We have a green glass case that we can see through. Let's forget the case. That's just a rectangle which is holding the liquid in it. The water, let's say it's water level. The liquid level is up to the blue here, and I'm going to keep this very simple right now. I'm just going to look at a rectangular cross section of material which starts at the top of the surface here and goes down a depth h, or a height h. And so we have a volume here, which of course is just h times a. That's the area times the height of this rectangular solid. And we know that that has a certain amount of mass, so it must have a certain amount of gravity acting on it. M times g. It's a certain mass which we'll be able to figure out very easily. That's just the volume times the density of this material. Rho times g. Rho times a. We multiply it times g. There's your force of gravity. And this gravitational force is pulling it straight down, and it must be exactly balanced by some other force that's pushing it straight up. What is the other force? We're going to ignore any force at the surface here, in this case, because there's no fluid above it, just air. I'm going to ignore that for the moment. There is water underneath the water in our cube, and obviously that water underneath here must be under some pressure. And the pressure acts in all directions, and in particular there must be pressure coming up, remember, perpendicular through the surface. So there must be a perpendicular force through this. This is an imaginary surface A here, where I'm going to do my computation. But running through that surface A is a pressure of the water underneath. In other words, the pressure down here at the surface A has to be large enough to exactly compensate and exactly equal the gravitational force pulling this whole cube down. That's what holds the fluid up. It's the pressure of the fluid underneath it. And so you can see how this works out in the formula, or you can see it intuitively. The deeper you go down in a liquid, let's say, or a fluid, let's say it's water, the deeper you dive down in the fluid, the more the pressure builds up. It builds up linearly with your depth. But we can see that exactly here. Here's my definition. Pressure is just force divided by area. The force we're worrying about here is the force of gravity. That has to be compensated by the pressure at the bottom of the box here. There's your M. It's just the density times the volume is AH. The density times the volume. Rho AH is the mass. mg is up there. G, 9.8 meters per second. And then we divide that by A. And then you notice something very sensible here. Notice we got an A on top and an A on the bottom, because the force is proportional to how big the box is. The pressure divides out by that area. A cancels out. The exact area of this box, this computation, doesn't matter. In fact, the exact shape of this box doesn't matter either. I just picked a rectangle because it was very easy to calculate. Little cubes are easy, but it could have been a cylinder. It could have been some really weird shaped box. It doesn't matter. Here's your general formula. The pressure as you go down deeper in this fluid has to increase with the depth linearly. The pressure has to be rho times GH. Now in these sets of problems, I think pretty much all the problems we're going to do in 6C, I'm going to ignore the possible variations in rho. That's a pretty good approximation for water. You can pretty much ignore that. So this is all going to be about 1,000 kilograms per cubic meter, and so rho would be a constant. And I'm also going to ignore the variations in G, because we're just doing this at sea level, and so rho and G are constants, so the pressure just builds up linearly as you go down from no pressure at the surface. Why is that? And everybody knows this who's ever dived down in a swimming pool. Any kind of diver notices. As soon as you start going down a few feet, a few meters, more meters, there's more water on top of you, and all of that water, a column of water, is pushing down on your body, pushing down on your head, pushing down on your sinuses. The deeper you get, the bigger the column gets, the more weight pushing down on you, the more pressure you're under. And that's the equilibrium condition, that pressure goes up as rho GH. And notice in this formulation here, you do have to watch out for the sign. We've defined H to be 0 at the top of the fluid, and as you go deeper, as you actually go down in the y-axis, H gets bigger here. It says that. H is the depth from the surface where the column starts. We're ignoring any weight of air that might be on top for the moment. We'll talk about that later. So there's our formula, and it's just the condition of hydrostatic equilibrium. Now, just to see that that works, that it doesn't depend on the area, it doesn't depend on the cross-section, doesn't even depend on the shape of the container. Here's a classic example. I'll try to do this one in class. Suppose I pour water, actually it's with some blue dye in it, so it's all a uniform density of liquid, and I pour it into complicated containers which are all connected at the bottom here. So then there's a certain amount of pressure at the bottom here, which is what? It's just the height from the top of the surface of the water down to the bottom times rho, the density of water, times g, the gravitational acceleration. So for all of these different tubes, the pressure difference from the top to the bottom has to be the same. So let me just go back to the other side. That's why the surface of water is always flat. It's always the same distance away from the center of the Earth, from the direction gravity is pointing. So that's true in this next slide too. Here, all of these tubes, then the fluid has to rise to the same height because they're connected at the bottom. What would happen if, weirdly, this tube were lower? The blue fluid were down here. Then the pressure of these other columns of fluid would push it back up and they would lower down. So they all have to come into equilibrium here. That's what hydrostatic equilibrium means. So that's why all of these levels have to be at the same height. That might be useful. It might help you solve some problems where we have a complicated geometry, because this is a very simple thing that they have in common. So now let's see if we can actually solve a problem. This is not too complicated an example, but it captures a number of the important points. Let's suppose you ever been on a farm and you know that they keep the water in a big water tank. They usually put that water tank to store the water up some scaffolding, so it's fairly far up in the air there. So there's generally, I don't know if they're this high, this is quite an elaborate one, but there's some height which the water has to run down or fall down before it comes to the place where the user gets it, for example, at a kitchen faucet. So this is, like I said, a pretty extreme engineering situation here. We want to have some water pressure probably, so the water will spurt out of the sink or the shower or whatever we're using. I don't know if we really would want this much pressure, but let's just do a simple example where you have to measure from, remember, it doesn't matter about the exact shape of the water, it's just the height from the top surface of the water down to the point where you want to measure the pressure. Right down to there where that cross is, because the sink comes out at that level there. Doesn't really matter how the water got there. It doesn't matter what the shape of this container is. It could be a cylinder that goes all the way down to the ground. It could have a funny shape. It could just have a pipe going down here. It could go underneath the ground and then come back up. Doesn't really matter. It's really because it's conservation of gravitational potential energy. The only important difference is the difference of gravitational potential energy from here to here, which we're told in this problem is 30 meters. You don't need to worry about anything else. Then I can tell you what the water pressure is at the sink in this little farmhouse on the prairie. Do they have a lot of water pressure? Yeah, if they have a 30-meter high tank, they have a lot of water pressure. Plenty, actually. Let's just work it out. Rho, G, H. What's rho for water? 1,000 kilograms per cubic meter. G, 9.8. For me, 10 is the same as 9.8 to astronomical level of accuracy. I'll give you full credit if you say 10 meters per second per second. H, in this problem, 30. Let's see, 30 times 10. 300,000 pascals, 300,000 newtons per square meter. That is really a lot. Wow. And as I said, if we're ignoring the friction or viscosity here, it doesn't matter how many pipes there are that bring it eventually to your sink, doesn't matter what path they take, doesn't matter if the pipes spiral around like I showed you in the previous slide. This is your answer. You're going to end up with sink pressure there of 300,000 pascals. All right. Now, here's the only thing that gets a little bit complicated. This is the only thing where you actually have to compute an integral here. But it's pretty important, so I want you to understand this. Let's now look at a little slab of water, fluid, that's just floating there, hydrostatically, so there's an equilibrium condition. And we just said that, let's look at the pressure. This is a very thin slab. It's only dy thick. We look at the pressure on the top surface of it. This has a cross-sectional area A. This is not a great diagram here. We're looking at it sideways. But let's say it's a disk or something. And so it's got an area A, and so that means the pressure of the water on top of it is bearing down with P. And so the force on this entire surface is P times A. What about the force on the bottom surface? We also have an area A, but the pressure, since we're at a deeper level of water, a little bit deeper, there's more water pressure coming in there, and this is maybe a little bit counterintuitive. That means there's more water pressure pushing up through the bottom surface of this. So P is a little bit higher here because it's a little bit deeper. We'll see by how much. It's just by the additional amount of depth. So this is somewhat drawn to, correctly here. The pressure pushing up on the bottom surface has a bigger pink arrow. That force, is shown by the pink arrow, is systematically bigger than the pink arrow pointing down on the top surface. There's a net force, because the force down is less than the force up here. There's a net force. Uh-oh. Does that mean we're out of equilibrium? Does that mean that this slab of water is going to start spontaneously accelerating upward? No, of course not. I left out one other force. What was the force that I left out that exactly offsets and compensates that extra pressure force? Pardon me a second.